Good afternoon, everyone. Can you hear me?
ได้ยินค่ะ
Okay, ขอบคุณครับ Okay, so yeah, nice to meet you all again for today's topic. Okay, let me share about my screen. Okay, well, let's get started with this topic. The today's topic, I'm gonna talk about catheter techniques for electrophysiology study. With me, Papum Dajidisili, a cardiothoracic technologist from Cardiovascular Center, Julapon Hospital. Some people may have a question about my experience. I used to work as a clinical specialist. That at the time I had to do something like to do 3D mapping for cardiac arrhythmia and to do definitely at that time I worked in a company such as I work in a Biosim Webster Johnson & Johnson company. Yeah, that's it. So today I have been invited to teach you or to talking with you about the techniques for EP catheter. For the outline, today I'm going to talk about cardiac conduction system first in order to review just a little bit before going deeply into the application of the cardiac electrode or I mean about the EP catheter, something like that. Okay, and the second, I'm going to talk about the setting of stimulation and electrophysiological workstation. Then we're gonna get through about the approaches for catheter access, and then EP catheters, electrode. After that, I'm gonna to know about the electrode configurations, the polarity, the catheter positioning, and the last one is about the basic electrophysiology study. Okay, well, let's start with the cardiac conduction system. As you know that the heart rhythm is our heart will beat at around 60 to 100 beats per minute, and definitely the electrical impulse, the first electrical impulse will be generated from a group of special cells that that is at the area around the upper area of the right atrium, which has the junction between the right atrium and the supraventricular and SVC. Let's say that superior vena cava. Okay, at that area we can specify more specifically as crista terminalis, right? So the special fiber or special cell of that group is called SA node. And after the SA nodes generate the electrical impulse, and then the electrical signal will spread throughout the SA node and spread through the RA or right atrium through the internodal pathways over here, internodal pathway, and go to the AV node and another pathway to depolarize the left atrium. The electrical impulse will go to the left atrium through the Bashman's bundle. All of these pathways, the purpose of this is just to let the both atriums can depolarize simultaneously. Okay, and after the electrical impulse go to the atrioventricular node over here, the impulse will stay here for a while, just like to, let's say about, it will be delayed just a little bit in order to make the atrium pump the blood into, in order to let the blood into the ventricles. And after that, the ventricle pump out the blood into the systemic or pulmonary system or something like that in the different phase to let them function, can function well. And well, okay, after the electrical impulse stay for a while at the AV node, the electrical impulse will go to the ventricle through the only pathway that is connected between the atrium and the ventricle. We can say that this is the only way that will allow the electrical impulse from the atrium goes down to the ventricle. It is called bundle of his. And after that, the electrical impulse will separate into two branches, which are called left bundle branch and right bundle branch here. After that, the electrical signal will go to the Purkinje fibers, and after that will go to the myocardium and cause the both ventricles contraction. Okay. Let's look at this correlation between the electrical activity within the heart and the body surface ECG. Definitely, after the SA node generate an electrical impulse, it will cause the onset of the P wave. And after the electrical impulse from the SA node spread throughout the right atrium and left atrium through internal pathway and the Bashman bundles into the left atrium, it will cause the atrial depolarization, right? So it will cause the P wave on the ECG. And after the electrical impulse goes to the AV node and stay at the AV node for a while, or let's say it is delayed for a while, we can see about this activity about at the time of PR segment. The PR segment, it means that there are some activities at the AV node. That means about the time that electrical impulse go to the AV node and stay delayed for a while, and after that we'll go to his bundle. After that, go to the left and right bundle branch, and then go to the Purkinje fiber before the myocardial of the left and right ventricle will cause depolarization. So all of this period will show you at the PR segment. Okay. And after the electrical impulse cause the ventricles, both ventricles contraction, it will show you about the QRS complex on the body surface ECG. At that time, definitely at that period, both atria will be in a period of atrial relaxation. So on the body surface EKG, you won't be able to see about the atrial relaxation activity that will appear on the body surface ECG because the QRS complex is covering all of the activity at the time. Okay. After that, after the ventricular depolarization, it will go to the ventricular repolarization. So at this period, you can see about the ventricular relaxation on the body surface EKG at the end of the QRS complex until the end of the TREV. Okay, this is an animation that is showing you about the conduction system, the normal conduction system that SNO generate SNO generate the electrical impulse and then spread out the electrical impulse throughout the atrial and cause the atrial contraction or depolarization. After that, the electrical impulse will go to the AV node to stay at the time for a while or to be delayed for a moment. And after that, the signal goes down to the left and right ventricle through his bundle that separate into left and right bundle branch, go to the Purkinje fiber that attach to the myocardium and cause the ventricular depolarization for both left and right atrium simultaneously. Okay, it will cause like this as a circle. Well, after you can review just a little bit about the normal conduction system. I'm gonna take you to see about the setting of stimulation and electrophysiological workstation. Well, the stimulation and electrophysiological and physiological monitoring, you can see about the diagram that I'm showing you on the screen. You will see about the patient lie down over here. And to prepare the patient, you're gonna have to attach the defibrillator patch first because you are working with cardiac electricity, so it can cause anything just like ventricular tachycardia or maybe something to cause the bradycardia. So defibrillation patch is the first. Consider that you're gonna have to place that patch on the patient's chest or on the patient's body, and after that, the other important things is that about the surface ECG patches, you're gonna have to place the ECG patches on the patient's body as well in order to monitor simultaneously with the intracardiac signal. Okay. Apart from that, you need to place a ground patch that often be placed at the height of the patient over here, and then the ground patch will be connected to the ablation system that I'm gonna show you in the later again. Okay. Okay, well, all of this that I described you is about how to prepare the patient. Okay, and what about the how to prepare the workstation? Definitely, you're gonna have to prepare about the junction box that will be placed beside the table in order to, because the junction box will be connected to the stimulator and the RF generator again, because junction box as the junction box will be connected with the all of the diagnostic catheters that will be inserted into the patient's heart to receive the intracardiac signal. So after the junction box is connected, the signal will go to the filters amplifiers that is connected to the junction box. Okay, after the signal goes to the filters amplifiers, the signals will be clean, just because of the filters will try to filter or clear out the noises and try to ignore any signals that we are not interested in. Okay, and again with the amplifiers the amplifiers will help to try to amplify the low amplitude that often get less than 10 millivolts, let's say, because the signal that from the body surface EKG and the signal from the intracardiac signal, the amplitude is often less than 10 millivolts. So the workstation need to, if you want to see about the signal showing you on the screen, the workstation need to use the amplifier to amplify or to increase the size of the amplitude to help you see about the electrogram on the screen again. Okay. After the signals is cleaned and amplified, that signal is analog signal. So the workstation, the system will try to transform the analog signals into the digital signal, and then you will be able to see about the intracardiac signal showing you on the real-time display over here. And after you update the screen, all of the updated data from the real-time display will show you on the offline display, and you can measure or you can access any important values that you need to tell the doctor about the values, the normal values that you can access from the data you get. Okay, this is an example of EP workstation from Boston, which its name is BARD, B-A-R-D, BARD. The BARD workstation, you see about this amplifier. Okay, let's start from the diagram again to make it more clear. Okay, after the patient here is after the patient is prepared with the defibrillation patch placed on the body and all of the EKG surface patches attached to the body already, and the ground patch as well. All of that things will be connected to the amplifier. Can you see this? The junction box is over here, the number 5. The junction box will be connected to the filters amplifier over here, the number 5, right? And the body surface ECG, the number 2, will be connected to the amplifier as well. This one. And what about the stimulator? Yes, definitely. The stimulator. Let's see about this workstation. The stimulator is on the right. On the right of the workstation card here. This is the stimulator. I'm sorry. This is the stimulator. The stimulator will connect to the amplifier through this port. The port 4 here. Okay. And after all things connected to the filters amplifiers, yeah, the function of the filters amplifiers will try to filter all of noise and the uninteresting signals that you want to see, you don't want to see, and try to amplify or increase the amplitude from the low amplitude that the catheter or the system receive from the body surface ECG or the intracardiac signal. After increase the size of the amplitude, then the system will transform the system will transform the analog signal into the digital signal and show you about the electrical activity on the real-time display on the left side, on the left screen here. And after you update, you can use about this keyboard to update about the activity on the screen in order to make it show on the offline display and try to measure any values to identify about the abnormality of the conduction system. This is the basic setup of the stimulation and electrophysiological monitoring. What about the ablation system connection? Because you won't see about the RF generator that will connect to the filter amplifiers over here, right? Because I haven't talked about the ablation connection system. that will connect to the amplifier here. Interesting, because this is the ablation system, and how to, because okay, let's say the ablation system will be connected with the ablation catheter. After the ablation catheter is advanced into the heart chamber, you see about the connector here will connect to this one, and how you can get the electrical signal to show you on the screen, right? If you have a question about this, definitely you will see about you will need to find about the connection between the ablation system and the amplifier that is a junction that you can connect between two systems, which is about this cable. This cable will connect this port here, which is a part of the ablation system, and then you can see about the 4-pin here, right? About the 4-pin here will be connected to the junction box here. That's it. All of the electrical signal will from both diagnostic catheters and from the ablation catheter can show you on the screen. Or I mean about all of the catheters can show you on the screen, just like this. This is about the system connection guideline to make you understand comprehensively about how to set up the workstation with ablation system. Okay. So far, anybody have any questions about what I have talked about?
อาจารย์ครับ
ครับผม
Can you please explain once again ablation system connection? The previous slide.
Okay. Well, from this slide, this is the ablation system, right? The ablation system. This is the ablation system that you can manipulate to control about the power, the temperature, and you can see about the impedance inside the heart, while the doctor using the ablation catheter here advance or place in the heart chamber. If the question is how to show the signal from the ablation catheter, which is inside the heart, because at this slide I just show you about the diagnostic catheter from that, which I mean about the diagnostic catheter which in the patient's heart will be connected to this junction block, right? So if you want to get the signal to show on the screen, you're gonna have to make a circuit to make a connection between the ablation system, which is quite standalone over here, with this amplifier. So if you wanna see about the signal from the ablation catheter, you're gonna have to use this connection, additional connection over here. You can see that, okay. After the electrical signal from the heart get through the ablation catheter over here, just follow my arrow on the screen. After the electrical activation comes through here, and then it will be connected with ablation cables over here, and then connected to this port, right? The electrical activity at this time is at here, and after that you wanna connect with the amplifiers. You're gonna have to make a connection pathway to the amplifier. So the only way that you can make that connection, you need a special, let's say an additional cable with 4 pins here to connect over here, and then the 4 pins here will connect to the junction box, and then the junction box will receive the ablation signal. After receiving that, the signal will be in the circle or in the process of filtering and amplifying the signal and showing you on the screen here, right? And that's it clear?
Yes, Ajahn. Thank you.
Okay. Any questions? Okay. Well, the most important thing that you shouldn't forget to use it is that the ground pad here, if you forget to attach the ground pad at the height of the patient's or anywhere of the patient's body, definitely after you using about the ablation catheter, the impedance won't show you at the time, and you can't ablate or do anything about the ablation catheter. Okay, just try to remember that when you try to prepare the patients in the laboratory, you're gonna have to first you're gonna have to place the defibrillation pad on the patient's body. After that, you need to place the ECG patches as well. And the most important thing about the last thing is that about the ground pad that you need to attach to the patient's body as well. There are 3 things that you're gonna have to always remember before starting the EP procedures. Okay. I think it will help you to more understand clearly is that about doing the lab in the real lab. I'm gonna show you again about how to set up the EP workstation to make you more clearly. Okay. If you wanna, if a doctor wanna insert about the diagnostic catheters or ablation catheter inside the heart, definitely the doctor need to find a suitable catheter access to approach the heart. The most common site for approaching the heart is that the femoral veins, which lie bilaterally in the groin region of the patient's hip area, which just lie medially to the femoral artery. at that area, the doctor can palpate about the femoral artery and try to puncture approximately approximately at the point 2 to 3 centimeter below the inguinal ligament. And okay, for this access will allow you to insert the catheter to advance up to the IVC or inferior vena cava and into the right heart. Okay, again with the femoral artery, the femoral artery will be located at the same side of femoral vein, but just like to not medial, just like lateral to the femoral vein, just a little bit. And at this side, the doctor will try to puncture 1 or 2 centimeter below the inguinal ligament, and just proximal to its bifurcation of the profunda over here, just proximal to the profunda and the superficial femoral arteries over here. So this puncture site is suitable for access site of the femoral artery. Okay, and this access approach can also this access site also can be called the retrograde approach that allows catheter to be advanced in retrograde fashion up through the aorta, across the aortic valve, and into the left ventricle. What about the other access site? In the past history, there is an exact site, just like internal jugular vein, that is offered to use to advance the catheter into the coronary sinus. But at the present, the internal jugular vein approach is not that common because it's quite difficult to manipulate the catheter into the coronary sinus or to do anything. So that's why the most common approach sites are just femoral veins and femoral artery. Apart from that, the subclavian vein is another approach that the doctor can use it to insert the catheter into the heart through the SVC into the right heart. But not that common to use at the present. Just like the multi of choice for the physician to choose the access site for any other opportunity. Maybe the doctor cannot use maybe the physician don't want to use the femoral approach to advance the catheter. Sometimes they can use the internal jugular vein or subclavian vein to insert the catheter instead. The last one is epicardial. The location of the epicardial approach site is that it is below the subxiphoid approach. The subxiphoid process which is a part of the sternum. I mean about the subxiphoid approach will help the doctor to advance the catheter into the pericardial space that the doctor, if the doctor need or want to map out the abnormal arrhythmia that occurs on the epicardium or the outer shell of the heart. Okay. Before inserting the diagnostic catheters or ablation catheters, we need something to just like to the opening way to let the catheters inserted through the vessels. We call them as sheath. The sheath, there are a lot of French size that the doctor can choose to choose to use in the case. The available French size of the sheath is around 6 to 8 French, are preferred in the EP lab. Okay, the 6 French will be green like this, and the 6 French will be green. The 7 French will be orange, and the 8 French will be blue, the blue one here. Okay, then EP catheters. After the doctor. Okay, let's try to make a story about from the approach side, right? After the doctor choose the appropriate approach of access site. Okay, let's say about the femoral approach. After the doctor puncture at that site, normally the doctor will use the femoral vein to insert the diagnostic catheter and try to place all of the standard catheter at the different sites inside the RA and the RV, right? If the doctor want to insert that catheter into the heart, they need some opening tract before insert into the vessel, which is a sheath. Okay, the doctor can choose any French size of the sheath depending on the size of the EP catheter as well. Okay, because the EP catheter the EP catheters from using are available from 5 French in to 8 French. So that's why the French size of the sheath can be available from 6 to 8 French. Okay, let's say about catheters. Okay, the electrode on the catheters, catheters used for electrophysiology study and ablation are composed of multiple insulated wires here, encased in woven dacron or polyurethane. The woven dacron or polyurethane is they are material for making the catheter shaft. Okay, so inside the catheter, you will see about the insulated wire that will be connected to each electrode on the EP catheters. Here, this is insulated wire, and the multiple insulated wires is encased in woven dacron or polyurethane, which is the shaft of the catheter over here like this. This is an example of deflectable curve. So you will see about the stainless wire braided here. Okay, the purpose of this picture, I just want to show you about the structure inside the catheter, about the insulated wire here that connected to each electrode, and then about the shaft of the catheter that is made of woven dacron or polyurethane. And the electrodes used in the electrophysiology catheters are usually made of platinum iridium. Here, the electrode here is made of platinum iridium alloy, because the platinum will the property of the platinum is high conductivity and radiopacity. High conductivity that can just like to faster in conduct the electrical from the tissue in order to conduct that electrical to the system. Okay, and what about the iridium? The properties of the iridium is just like to improve the mechanical strength. That means to increase the hardness of the electrode. Well, each electrode is paired with another electrode to record electrical information between the two electrodes, and can also send a pacing stimulus to the contacted tissue. This is the main function of any electrode pair can be used in the case. There are two functions that First, record electrical activity between the electrode pair, and second, to deliver a paced stimulus from order from the workstation. In the laboratory, there are multiple electrode configuration for multi of choice, and definitely that multi of choice must depend on the suitable way to use. For example, okay, the first one about the quadrupolar that has 4 total electrodes at the end of the catheter. The distal electrode is here is referred to as the first electrode, and the proximal most electrode we can say about the 4th electrode. Okay, actually the quad catheters are the most commonly used catheter of choice and have multi-use capabilities, because both diagnostic and ablation catheters often used for quadrupolar or 4 electrode catheter to access or to ablate the tissue, the abnormal tissue or something like that. The next one is decapolar. The decapolar means that deca is Greek, right? The deca means 10. So the decapolar has 10 electrodes on the catheter. Again, the distal one, the distal electrode is called the first electrode. The next one is second. After that, third, fourth, and until the proximal most electrode is called as the 10th. Okay, and decapolar catheters allow for the access of longer spans because there are a lot of electrodes over here, and so it's suitable for accessing a larger spans of cardiac tissue, which is commonly used in the coronary sinus. The hexapolar or octapolar, hexa means 6 or octa means 8. Definitely, if hexapolar, there are 6 electrodes on the catheter. What about octapolar? The octapolar has 8 electrodes on the catheter. Definitely, at the present, hexapolar and octapolar, we have hardly seen we have hardly seen about this catheter in the real lab because the doctor don't use them much in the lab, because the purpose of these catheters just to provide more electrodes and useful for structures like the His bundles, where a precise placement is critical. That means if the quadrupolar catheter cannot place, it's quite difficult to place at the His area. The hexapolar or octapolar are another choice for the doctor to use in order to place at that area with the complex anatomy or something like that. That is difficult to find the His area. Okay, and definitely these catheters can also offer more discrete and higher fidelity signal acquisition because of the multiple electrodes and the spacing, which is quite small, that I'm going to talk to you about these properties of the spacing again. Okay. The dual decapolar, there are 20 electrodes on the catheter. This catheter allows for assessment of large spans of cardiac tissue because it's quite large, right, about the catheter, so it can place and cover quite large area of the heart, within the heart. So it's very useful when the doctor are doing ablation at this to treat about the atrial flutter, the typical atrial flutter that will cause the electrical activity to make a macro circuit around the right atrium. So this dual decapolar catheter will help to identify the blockage or the activation sequence inside the heart during atrial flutter ablation or something like that. Okay. The special electrode catheter we often use when the more complex arrhythmias and locations in the heart are appearing. Let's say that because if the arrhythmias are quite more complex, or the location quite the locations are quite difficult to use the normal or the standard electrode in order to get into that area, the special electrode catheter often used instead, because the difference in designs can translate to faster and larger amounts of electrical data allocation. They also offer increased support for ablative therapy, tissue contact, or innovative ablation therapy such as cryoballoon. The picture at the bottom here, I just want to show you about the special catheter. The first catheter from the left side here is called basket catheter, which is a mapping catheter from, I'm not sure about. Okay, it is a mapping catheter for 3D mapping catheter. You see about that. You see about the electrodes. There are a lot of electrodes on the catheter over here. All right, and the second one is the lasso catheter. The lasso catheter is often used in AF or atrial fibrillation ablation case, to just like to map out about the interesting signal around the ostium of the pulmonary vein, something like that. Okay. The third one is HD grid. HD grid is a mapping catheter of Abbott or St. Jude. Okay. This catheter just like to map or to acquire the electrical signal inside the heart chamber to make it more faster and larger amounts of electrical data acquisition. Okay, and the last one is the Penetrate catheter. The Penetrate catheters is just like this. Let's say the Penetrate catheter is from Bios and Webster is a mapping catheter as well. To the doctor often use all of this to just like to acquire more electrical signal at the same time. If you acquire just one time, you definitely because of a lot of electrodes on the catheter, if after you acquire to get the electrical signal, you will get a lot of data from this catheter at that time. Okay, let's say about the catheter types. We have two types of catheter available in the market. There are fixed curve and deflectable curve. Definitely the fixed curve, a fixed curve catheter has a pre-shape curve that the physician can just place the fixed curve catheter at the area, at a specific area, and the doctor cannot manipulate the curve just like to extend or to deflect or something like that. Just like the deflectable curve here will come with the plunger handle. The plunger handle just like to manipulate about the deflection and the extension of the tip of the catheter to get to the anatomical landmarks. The black handle here is a sample of unidirectional curve, just like you can just push and pull, just like only push and pull to deflect the tip of the catheter. Not similar to the white handle one here. The white handle one, this handle is used to deflect the tip of the catheter in bidirectional way. You can see, and definitely you can see about the label on the handle here, that means this catheter can deflect from one direction into another one direction. With the deflectable curve, the unidirectional curve can be chosen from the range of A curve, B curve, C, D, E, and F curve. The more, I mean, that means the A curve, it just represents about the small curve, and the B curve is larger than the A curve. But the largest curve available for this sample, for this example, is the K black. About not K black. I'm sorry. About the F orange. The F orange will be very small. Larger curve, the largest curve, compared to the A wave, the A curve over here. Okay, let's say about the more letters in English, the bigger one becomes. Okay. This is an example of the available curves of the Biosen-Webster. When you go to the real EP lab, you may see about the curve that's not called like A, B, C, D, E, or F, just like sometimes it can be called as small, medium, or large curve for another company, not the Biosen-Webster. Okay, the deflectable curve with the bidirectional curve can be the F curve, FJ curve, DD curve, FF, or JJ. This is again with an example of the catheter of the curve from the Biosen-Webster or Johnson & Johnson company. The DF curve is a symmetric curve that the doctor can utilize from both curve from D or F, because the doctor can use both D curve to approach the anatomical landmark. If the D curve is not enough to get to that area, the F curve will be used instead, or something like that. This is the advantage of the asymmetric curve. Okay. What about this one? This one is, I just want to show you that from the curve from other company won't use A, B, C, D, E, F to call the curve, but they use standard the word standard or large radius curve instead of A, B, C, D. Okay. When it comes to about the catheter shapes, there are a lot of catheter shapes. Let's get to know about each one. Okay, the Josephson EP catheter or JSN. The Josephson EP catheter has a small curve for smaller areas that is useful to use in the area of H highlight atrium or placed in the right ventricular apex. D'Amato EP catheter has a large curve and is more amenable for the ventricle, the cornet. The D'Amato is over here. The curve is appropriate to, let's say about the curve is appropriate or suitable for placing the catheter inside the right ventricular apex. The next one is corner EP catheter. The corner EP catheter has larger curve that is amendable to the head. It's quite different from the Josephson, right? The Josephson is because the Josephson has a small curve. The angle of the curve is similar to the corner EP catheter, but the corner EP catheter has the larger curve. Is larger than the Josephson, right? So the larger curve is of the corner catheter is suitable to get to his area. Okay. The next one is Levine EP catheter. The Levine EP catheter has the same curve as the corner EP catheter, but it's larger than the corner EP catheter. Apart from that, will be about the special, let's say about this special catheter. The hollow EP catheter or the cup EP catheter is usually has 20 electrodes on the catheter. And that catheter may have a soft fixed curve or a deflectable curve, often used to freely position in large chambers to determine activation sequences, as I said before, right? About the activation sequences in the case of atrial flutter ablation, to see the blockage of the line ablation, or to see about the activation sequence that from the atrial flutter that try to spread out the right atrial. Okay. The next one is lasso EP catheter. The lasso EP catheter, the shape is spiral. The shape is spiral, and this catheter is often used for faster mapping and assessment of a pulmonary vein in the case of atrial fibrillation ablation. Okay, and the last one, basket EP catheter. The basket EP catheter has spherical shape with multiple electrodes on the catheter here, often used for fast and high volume electrical signal processing and acquisition. the catheter sizes. The EP catheters are measured in size French, where one French equal 0.33 millimeters. In the laboratory, most EP catheters can come in sizes of 5 to 8 French. Let's say the larger the French size, the stiffer the catheter becomes. Okay, if the doctor want to afraid of ventricular perforation or right atrial fibrillation from placing the quadrupolar diagnostic catheter with 6 French, maybe the doctor will consider to use the 5 French instead to avoid perforation, that perforation. But actually, at the present, the doctor can have multiple choice to use the French side of the catheter. The diagnostic catheter often used in 5 to 6 French. Is the 5 and 6 French diagnostic catheter often used in the real case. When it comes to about the 7 or 7.5 or 8 French is often used as ablation catheter. Okay, the key point of this slide, I just want you to know about the larger of the larger French side will make the catheter to be stiffer. Okay, if the doctor want to avoid the complication like perforation of the chamber, definitely you can suggest the doctor to decrease the size into the 5 French. The doctor to avoid that complication. If the catheter is not stable and need more stiffer, definitely you can suggest the doctor to use the bigger size, just like 6 French or 7 French of the diagnostic catheter to be able to more easily manipulate or place the catheter into the destination position. Okay. Okay. After you know all about the importance of the electrodes which are on the catheter, you need to know about how to connect the diagnostic or ablation catheters to the workstation or to the system. Definitely, we have a connection cables available like this. Okay, the cables with 4 pins showing you on the screen here is an example of connection cables for diagnostic catheter with quadrupolar catheter. Okay, if you want to connect the cables with the decapolar catheter, definitely you can't use the 4 pins connection cables here to connect the decapolar catheter to the junction box. You're gonna have to change to use the 10 pins connection catheters. 10 pin connection cables instead. Okay, the number of the pin depending on the number of the electrodes on the catheter that the doctor is using. You're gonna have to match to try to match that point. Okay. Okay. This connector, this is an end connector will connect to the end of the catheter here, and the pin, this pin will connect to the junction box. The below picture here is another example of ablation cable, let's say, because the ablation cable, you're gonna have to let's say the ablation cable will be the direct cable to connect from the end of the ablation catheter, and another of the cable will connect to the ablation system. Let me show you again with this picture. That cable is here. The cable, the one of the cable will connect to the ablation catheter, and the another one will be connected to the ablation system here. And of course, if you wanna see the ablation, the electrical signal from the ablation, you're gonna have to connect the ablation system here to the junction box with these 4 pins, just like to make a connection between the ablation system to the junction box to see the ablation signal. Okay. Well, after we all know about the catheter shapes and catheter size, we should know more about the electrodes on the electrode catheters. Okay, the distance between 2 sequential electrode pairs is referred to as electrospacing. The smaller the distance of the space, that means the more discrete, more detailed, and higher fidelity of the electrical signal recording becomes. Okay, just like if the smaller spacing, electrospacing here, the smaller will help you to see more more discrete and more detailed about the signal that we receive from the catheter. If we use the bigger about the electrode spacing, the distance between 2 pairs of the electrode, which is bigger, will make more losing about the detail of the data. Okay, so the main point is that if you wanna see about the electrical signal, which is more, you want to see it's more clearly, and you want to, because let's say if you want to see more clearly about the signal from the heart, you need to use the small distance of the spacing. If you don't care about the electrical signal receiving from the cardiac tissue, you can use the bigger, the spacing which is bigger, just like 5 millimeter or 10 millimeter instead. Okay. The sizes of spacing are measured in millimeters, and the common electrospacing size are available from 2 to 5 millimeter spacing, but actually 10 millimeters at the present is used as well for RVA catheter. Okay. Let's say the difficult tissues to measure, like the his bundle, may require tighter spacing for cleaner and more discrete signal acquisition, just like 2 millimeter spacing to use to get more detail, to get more cleaner signal, to get more discrete signal, something like that. Let's start with 2 millimeter spacing. Definitely, it's useful when precise local mapping is needed to pinpoint location during ablative therapy. And sometimes his bundle can use the advantage of the 2 millimeter spacing to place at his bundle if his bundle location is quite more complex to place to use the standard, just like the quadrupolar with 5 millimeter to place or to find that area. We can use or it's quite difficult to find his bundle or his signal, the 2 millimeter spacing catheter. It will be useful for this kind of situation. The coring sinus and ablation mapping catheter utilize 2 millimeter spacing configurations in the real case, so it provides the most discrete and cleanest signal detail. The 5 millimeter spacing. It is commonly used in chambers with low amplitude electrical signals, such as in the RA or RV. But actually, in the RV, the doctor often use the 10 millimeters instead. The 252 millimeter spacing. Sorry, with this picture, the 252 millimeter spacing will be like this. Okay. The benefit of using this spacing catheter, because it provides the advantage of both 2 millimeter and 5 millimeter spacing. That means the spacing of 2 millimeter offers the most signals, and the 5 millimeter spacing covers a larger area of cardiac tissue. This spacing configuration is often found in CS, as told you before, and as well as about the ablation or mapping catheters, because the ablation and mapping catheter need to pinpoint the precise location of the ablation, right? So the 2 millimeter spacing catheter, the benefit of the 2 millimeter spacing is suitable for that purpose. The wide spacing or 10 millimeter spacing, we often use this spacing with the RV with right ventricular apex catheter because the doctor don't want to see the clear detail to see that clear detail, just like to use the RV catheter or 10 millimeter spacing catheter to paste or stim, just like to paste the RV to paste to paste the ventricle, just like that, because the doctor don't want use it to see more detail about the signal, just like for stimulus pacing. The electrode tip of the diagnostic catheter is generally 1 to 2 millimeter wide, but definitely depending on each manufacturer. When it comes to about the ablation tips, it comes in size of 3.5 millimeter, 4 millimeter, 8 millimeter, and 10 millimeter. The larger ablation catheter tips can burn larger areas of tissue. This is the main point of using how to choose the appropriate ablation catheter to match with an ablation technique or something, just like that. Okay. The electrode tip of an ablation catheter comes in a variety of sizes depending on the tissues arrhythmia to be calculated, arrhythmia to be ablated, and the ablative energy used. If, let's say, if that tissue, that abnormal tissue that the doctor want to ablate on, that ablation tissue is quite thick and need to use the high power or high temperature. So the size of the ablation tip should be bigger, because the bigger size of the ablation tip will help you to provide more ablation energy. Okay, for example, if the doctor if the doctor need to choose an ablation tip catheter between 4 millimeter and 8 millimeter to ablate on the carbotricuspid, it must for the typical atrial ablation, right? If the doctor want to use to ablate on that area, which is quite thick, definitely that area, the doctor need to use the higher energy or power to destroy or to burn that area, right? If the doctor want to use the higher energy, definitely when compared with 4 millimeter and 8 millimeter, 8 millimeter will provide the doctor with the higher energy to ablate on that area. Okay, and what about the 4 millimeter? The 4 millimeter will definitely we can say it is standard to use in normal, not normal, in general arrhythmia, just like SVT, let's say. The SVT ablation or atrial tachycardia ablation without irrigated tip ablation catheter, we often use the 4 millimeter and definitely the PVC as well. If the doctor want to use the standard or the standard ablation catheter tip with 4 millimeter, the doctor can use this size tip catheter to ablate SVT, AVNRT, AVRT, AT, or something like that. This picture, I wanna show you about the tip size with 4 millimeter, 8 millimeter, and 4 millimeter with irrigated tip. You see that if the doctor just like to want the target temperature that the doctor want to set up is 55 degrees Celsius, you will see that the 4 millimeter can provide just 15 watts to that tissue until the temperature of the catheter increase up to 55. And then see about the 8 millimeter. The 8 millimeter can use the power of 30 watts to destroy the abnormal tissue until its temperature higher up to 55 degrees Celsius. And you can see about the scar or the affected area of the ablation from both catheter. You will see that the 4 millimeter it's not that deeper as the 8 millimeter that can provide the deeper lesion to the cardiac tissue. When it comes to about the 4 millimeter with irrigated tip, this is the target temperature is 55, right? The 4 millimeter with irrigated tip, the target power 30 watt as well as the 8 millimeter. The 4 millimeter with irrigated tip, just the temperature of this catheter just high up, just increase up to 43 degrees Celsius with the same length, of the tissue lesion, cardiac tissue lesion here, but the length, the wider, let's say about the wide of the lesion, just like will be just like cephalic, just will be like not, let's say not wider like the 8 millimeter that spread out from the catheter to the around area like this. But if the doctor uses a 4 millimeter with irrigated tip, because of this saline in the catheter, from irrigated tip will help to maintain the lesion, to shape the lesion just like to be like this, to, let's say, to make it more deeper in lesion but not wider. Yeah. Okay. The final one for the electrode, we are going to talk about the polarity. The polarity an electrogram inside of the heart measures the depolarization of cardiac tissue between electrode pair, right? So if an electrical signal or activation is moving towards the electrical pair, it will cause a positive deflection on an electrogram, just like this. But if the electrical signal or activation is moving away from the electrode pair, definitely a negative deflection will appear just like this. If the electrical signal or activation is moving toward and away from the electrode pair, it will show you as a biphasic signal like this, okay? The polarity we can describe into unipolar and bipolar. Unipolar means that the catheter means that the electrode means that there is one electrode in contact with the heart. For example, the distal electrode 1 is contacting with the heart tissue, and the other electrode is outside of the heart or on the surface of the body. Just let's say if we are looking at the distal electrode or the first electrode will make itself as a positive pole. Okay, make itself as a positive pole, and the electrode out of the chamber of the heart or outside of the heart will be just like the reference electrode, let's say 0, to be a ground, to be 0. So to cause the first electrode on the catheter to be just only positive pole. Okay. If the electrical signal move forwards or move away or move forward and away from that electrode, will cause the characteristics of the unipolar of the let's say on the electrode you are focusing on. Okay. Since a unipolar configuration spans a large area of tissue, you can see about the green one here. This is showing you about the area of unipolar to receive about the signal from electrical tissue from inside the heart. Okay, this is the area of affecting unipolar. It is susceptible to far-field, low-amplitude ventricular depolarization and environmental noise. Let's say the green one here, you can see the radius and the area of the green one here. So you will see that the green one is covering the ventricle as well. So on the unipolar catheter, the unipolar determine about the first one. The unipolar proximal one is the first, right? So the unipolar catheter can detect both the signal from the atrium and the signal from the ventricle as well, just like this. Actually, the unipolar recording offers a unique advantage in mapping and ablation, as the signal of interest is acquired from only the tip of the catheter electrode rather than from a combined bipolar signal, yielding pinpoint location for discrete arrhythmogenic foci. This is the advantage of the unipolar when the doctor is ablating the arrhythmia from a force from, let's say, about the arrhythmogenic foci, means that there is abnormal electrical signal impulse generated from an abnormal group of cells, just only one group, or just only one group, or just, let's say, about group area, something like that. So the unipolar will be beneficial for that performing, because the catheter can be placed on that point, and that point, I mean that the abnormal area, and if the unipolar signal appears just like the QS shape. QS shape mean just like this. Mean about the negative signal showing you on the unipolar. That means, and that area is originating the abnormal electrical impulse, and then generate the and spread out the electrical impulse throughout the myocardium, something like that. If you still remember about the unipolar, which is a positive pole, right? If the electrical impulse move away from the positive pole, it will cause the negative deflection of the signal on that electrode. Okay. The last one is about bipolar. The bipolar recording is the most common and widely used method of recording electrograms. because the bipolar will record the voltage difference between the two electrodes on the electrode pair. And the bipolar recording offers more discrete signal acquisition and less far-field activity inference. How to decrease the far-field activity interference? Let's see about the green point here. The green point here is just the area of detecting or recording the electrical signal because the bipolar means will work just like to record the electrical activity between two electrodes, just like this. The recording will work at the distance here. So the area of recording is very small, so that is showing you just like the green point here, that not similar like the unipolar that is covered large spans of the cardiac tissue. That means including about the left ventricle or left ventricular activity as well. That's why the unipolar can detect the ventricular signal over here, not like the bipolar that the recording just only detect or record around at two electrodes here. So the signal showing you on the screen will show you just only the signal, which is more discrete, that tell you about the exact cardiac tissue location. For example, this is from the high right atrium. It only show you the atrial signal. Sorry. Anybody have any questions about all of the EP catheters and the electrodes, or even bipolar or polarity so far? Anybody have any questions, or anybody want me to describe more about anything before going to have a trick debate? มีไหมครับลองสงสัยไหมครับ
อาจารย์พูดเรื่อง QS shape อีกรอบหนึ่งได้ไหมคะ
อ๋อได้ครับได้แต่ว่ามันจะเกินขอบข่ายเนื้อหาไปหน่อยนึงนะแต่ที่เขาเสริมที่พี่เสริมไปคือเสริมมาให้แบบจะได้รู้เหมือนกับว่าพอเข้าใจนิดนึงเนาะคือพูดไทยได้ไหมอันนี้เดี๋ยวนะเพราะว่า QS shape ใช่ไหมฮะ QS shape คือมันจะเป็นลักษณะของอิเล็กโทรแกรมที่จำเพาะสำหรับยูนิโพล่าครับเพราะว่ามันจำเพาะยังไงเพราะว่าเราลองมองไปที่ยูนิโพล่าอิเล็กโทรดนะเรามองพอพูดคำว่ายูนิโพล่าอิเล็กโทรดเนี่ยเรามองที่จุดเดียวใช่ไหมเรามองที่ขั้วเดียวแล้วกันเราสมมติเราไปที่เราบอกว่าเราจะให้distal electrode ก็คืออิเล็กโทรดที่1อ่ะเป็นยูนิโพล่าเราจะโชว์มันอ่ะเราก็จะมองแค่ยูนิโพล่าที่1เท่านั้นใช่ไหมฮะพอเราบอกว่าให้1อ่ะเป็นยูนิโพล่า1ก็ทำตัวเป็นขั้วบวกใช่ปะพอ1เป็นขั้วบวกปุ๊บแล้วอย่างที่เขาบอกว่ามันจะต้องมีตัวอื่นให้เป็น reference เหมือนที่เวลาเราเรียน EKG เนาะมันจะมีเราก็จะบอกว่ามันจะเป็นที่แบบ unipolar ของดีด AVR AVL AVF อย่างเงี้ยมันก็จะทำตัวเป็นขั้วบวกใช่ไหมแล้วมันก็จะมีตัว reference โดยที่เครื่องมันจะทำหน้าที่ในการหาค่าแล้วในการ sum average ต่างๆออกมาแล้วการเป็นค่าศูนย์คล้ายๆกันอันนี้ก็คืออันนี้ก็เหมือนกันมันก็จะบอกว่าให้เครื่องEP เป็นทำหน้าที่เป็นศูนย์ใช่ไหมแล้วให้ตัวหมายเลข 1ที่เรามองเนี่ยเป็นขั้วบวกพอขั้วบวกปุ๊บลองนึกสังเกตดีๆนะตามที่พี่อธิบายไปก่อนหน้านี้ว่าสัญญาณไฟฟ้าอะไรก็ตามมันเหมือนกันเนาะมันเหมือนกันก็คือสัญญาณไฟฟ้าอะไรก็ตามที่วิ่งเข้าหาขั้วบวกมันจะทำให้สัญญาณเนี่ยเป็นบวกถูกไหมสัญญาณอะไรก็ตามที่วิ่งออกจากขั้วบวกมันจะแสดงตัวออกมาเป็นลบแต่ถ้าเกิดสัญญาณก็ตามสัญญาณใดก็ตามที่วิ่งเข้าแล้ววิ่งออกมันก็จะออกมาเป็นบวกและลบอันนี้คือหลักการง่ายๆของการเดินของสัญญาณไฟฟ้าเนาะที่จะโคแบบเป็นบนสัญญาณนะครับฉะนั้นแล้วถ้าสมมติว่าเราเอาไอตัว unipolar เนี่ยลองนึกนะไปวางไว้อยู่บนที่มันเป็นที่มันสร้างคลื่นไฟฟ้าหัวใจที่ผิดปกติอย่างเช่น PAC หรือ PVC ที่มันเป็น foci อันนี้คือ focal arrhythmia เนาะก็คือ focal arrhythmia ก็คือมีกลุ่มเซลล์กลุ่มหนึ่งจุดเดียวเลยสร้างไฟฟ้าขึ้นมาแล้วก็ปล่อยมันออกไปปึ้งใช่ไหมฉะนั้นถ้าเกิดว่าแสดงว่าการที่มันปล่อยไปได้น่ะแล้วมันก็ทำให้เกิด PVC เกิดขึ้นหรือ PAC เกิดขึ้นนั่นหมายความว่ามัน control heart rate ของหัวใจเราและในช่วงเวลาหนึ่งถูกไหมครับเพราะว่าถ้าเกิดมันเต้นได้แสดงว่ามันไปกด SA node นิดนึงใช่ไหมมันก็จะเกิด compensatory pause หรือ pause อะไรต่างๆตามมาไอ้พวกเนี้ยฉะนั้นแล้วถ้าเกิดเราเอา unipolar ไปวางไว้บนจุดที่ผิดปกติเนี่ยสัญญาณไฟฟ้าอย่าลืมนะถ้าจุดนั้นเป็นจุดกำเนิดไฟฟ้ามันจะต้องสร้างไฟฟ้าแล้วมันก็ปล่อยจากจุดของมันใช่ไหมให้มันกระจายตัวออกไปรอบข้างฉะนั้นจุดที่มันสร้างไฟฟ้ามันจะไม่มีสัญญาณที่มันวิ่งเข้าขั้วบวกเลยมันจะวิ่งออกจากขั้วบวกอย่างเดียวเลยนั่นมันเลยทำให้ตรงจุดนี้เวลาแพทย์เขาทำการจี้พวก PVC กันนะครับเขาจะใช้ unipolar มาเป็นตัวช่วยตัวหนึ่งเพราะว่าถ้าแคทเตอร์อยู่บนจุดที่มันสร้างสัญญาณที่ผิดปกติแล้วนั้นน่ะมันควรจะเห็นเป็นสัญญาณที่ไม่มี positive deflection บน unipolar signal เลยก็คือ QS มันมาจากคำว่ามันก็คือ QRS complex นั่นแหละถ้าเราบอกว่า Q เราคือเป็น negative ใช่ไหมแล้วก็ R คือเป็น positive แล้ว S ก็เป็น bigger negative ลงมาใช่ไหมครับอันนี้คือตามหลักของ QRS complex ฉะนั้นเราแค่ตัดตัว R ออกไปเพราะมันไม่มี positive ไงมันก็เลยเอา Q ที่เป็น negative บวกกับ R ที่S ที่เป็น negative อีกรวมกันมันก็เลยเรียกเป็นชื่อหนึ่งของ unipolar ที่บอกว่าเป็น QS shape เป็น QS wave QS wave มันก็เลยบอกว่าเป็นแค่ negative อย่างเดียวนั่นหมายความว่าตรงจุดนั้นแหละเป็นจุด on point ของแหล่งกำเนิดไฟฟ้าที่มันผิดปกติแบบ foci อันนี้เข้าใจไหม
เข้าใจแล้วค่ะขอบคุณ
โอเคครับโอเคขอบคุณครับมีคำถามอีกไหมครับถ้าไม่เข้าใจลองทำได้นะเพราะว่าจริงๆไอ้ที่เขาเอามาทั้งหมดนี้ครับก็พยายามเอาที่ไปเป็นเมนพอยท์ที่ควรจะต้องรู้จักแล้วก็ควรที่คือมันเป็นสิ่งที่ในห้องแลบจริงๆยังมันเป็นสิ่งที่ต้องรู้เนาะเป็นเมนพอยท์เขาอันนี้เอามาแค่เฉพาะแบบเนื้อทั้งนั้นเลยคือก็จะพยายามอธิบายให้ได้มากที่สุดเนาะโอเคงั้นถ้าเกิดไม่มีอะไรแล้วเดี๋ยวพักกันสัก10 นาทีไหมครับเดี๋ยวมาเจอกันตอนสักบ่าย3:10แล้วกันเนาะเดี๋ยวก็จะไปตะลุยเรื่องที่เหลือพาร์ทหลังๆก็ไม่ได้เนื้อหาแน่นขนาดนี้แล้วครับมันจะเป็นในเรื่องของ position และกันในการวางแล้วก็อาจจะพูดถึงเรื่องการวัดค่านี่นั่นต่างๆอีกเล็กน้อยเนาะมันเพื่อมันเพราะว่าเป็นการทบทวนแล้วกันไม่รู้ว่าก่อนหน้านี้เรียนมาเลยหรือยังเกี่ยวกับเรื่องของการวัดค่า AH interval A อะไรอย่างเงี้ยครับผมมันเป็น basic interval นะที่แบบจะพูดถึงนิดหน่อย นะครับงั้นเดี๋ยวบ่าย3:10 นาทีเจอกันนะครับ
ค่ะ
Okay. Let's continue to the catheter position. The high-right atrium, that is a polar catheter. Let's say the diagnostic catheter that will be placed in the high-right atrium should be quite soft and pliable, because the right atrium, the wall of the right atrium is quite thin. So to avoid the perforation of the right atrium, the diagnostic catheter should be soft and pliable. And definitely a quadrupolar catheter will be used with 5 millimeter spacing to place in the eye, to be placed in the RA at the area of high right atrium, close to the SA node area around there. So let's see the picture here. This is the standard position of the high right atrial catheter. Should be like this. Okay. And this catheter will, as I said, we will place the catheter at the high right atrium to record the electrical activity from the RA in the direction of the high right atrium, in the area of the high right atrium. And after that, we will have another diagnostic catheter to place at the area of his bundle. As I said, his bundle electrode catheter should be just 5 millimeters with fixed curve, or if the anatomy of his bundle is quite complex to reach to with a fixed curve catheter, a deflectable catheter is another choice of the catheter to approach to his catheter area again, if the doctor need more discrete and detailed of his electrogram or signal at that area. Definitely the 2 millimeter spacing will be another choice. If there is another diagnostic catheter to record the electrogram from the left side of the heart. If the doctor want to record that signals, the coronary sinus will be the position to place a CS catheter inside, because the coronary sinus is a vessel, is a vein vessel, is a vein lying posterior wall, along posterior wall of the left atrium, between the left atrium and left ventricle, and lying in the groove of atrioventricular groove, right? So the CS catheter often has 10 electrodes on the catheter with spacing of 5 to get the electrogram from the left side of the heart. You will see from the picture, you will see that the end or the distal one of the electrode will be the most lateral of the left side of the heart, and the proximal electrode, the most proximal electrode, will be close to the septum of the right side of the heart. So if there are any abnormality, just like abnormality conduction, just like there is an accessory pathway from the left side of the heart, the coronary sinus can be used to access or to differentiate the to identify, let's say, to identify the location of that action of that accessory pathway from the left side. This is the beneficial of the CS catheter, apart from using it to recording the electrogram from the left side of the heart and pacing, but it can use to identify the accessory pathway from the left side of the heart as well. The CS catheter or a decapolar catheter, we often use the deflectable catheter because it's quite difficult to advance the decapolar catheter into the coronary sinus, because it depends on location of the ostium of the coronary sinus. So to make it more easily to advance the catheter into the coronary sinus, the doctor often use the deflectable curve catheter. Okay. For the diagnostic catheter in the right ventricle, we often place the a quadrupolar catheter with 5 millimeter or 10 millimeter to the right ventricular apex, where is the beginning of the contraction of the ventricular contraction. So and definitely, if the doctor want to stabilize the catheter within the right ventricle, because it's pump out the blood all the time from apex to the basal, right? So if the doctor want to need to stabilize the catheter, they definitely the RV apex is the most suitable position or location of the RV catheter to place on. The RVA catheter, the doctor often use a fixed curve with maybe Josephson or Conrad, that depend on the physician decision to use, right? The left atrium can be a position that the diagnostic catheter or ablation catheter can place inside the LA. but left atrium is not a standard position, a standard location for placing any diagnostic catheter, because we do not want to record any signal from that area in a standard EP study. In a standard EP study, we just need to place the high right atrium catheter at the area of high right atrium, the coronary sinus catheter in the coronary sinus, and the RVA catheter at the RV apex. And additionally, some EP lab, the doctor may use his catheter, which is a quadripolar, his catheter with steerable catheter, I mean deflectable. The catheter is deflectable, okay, to reach his area. There are just only 4 catheters are used in the standard case, but for the left atrium, we often use the ablation catheters or special catheter, just like lasso, to map out the interesting signal around the pulmonary vein, and the ablation can go to around the pulmonary vein to ablate around that air circle for all the pulmonary veins in the case of atrial fibrillation with pulmonary vein acceleration technique, right? So if the doctor wanna approach the left atrium, definitely he need to do more procedure, just like transceptor puncture, because transceptor puncture will be a procedure that just like to try to make a connection from the right side of the heart to the left side of the heart through the interatrial septum. In transceptor puncture procedure, we need a long sheath catheter, which is around 8.5 French, and the long it is around 63 centimeter in length, with the later and the guide wide will be 0.032 inch with 180 centimeter in length. This long sheath will be used to be an approach of the catheter into the left atrium. Another tool is that broken bowl needle. Broken bowl needle is a transceptor needle to use to puncture the area of in the interatrial septum to make a hole, and after puncture to make a hole, and then try to push the long sheet through that small hole to be the opening area of the catheter, to be the entering area of the ablation catheter or lasso catheter into the left atrium. Let's see about the transceptor puncture technique. Definitely look at the PJA. dilator and sheath are placed into the SVC here using a guide wire, the guide wire. And then a needle is inserted into the dilator until the SVC, you will see that the sheath, you will see that the long sheath with the needle inside the sheath, inside the dilator, the black one here, right? The doctor won't allow the puncture needle outside of the dilator while it's in the SVC. Okay, and then go to the picture D. The dilator with the sheath, the dilator and sheath will be pulled down from the SVC into the interseptum with 2 drop. Let's say 2 drop because the first drop will be the big drop, because the drop is from the SVC into the right atrium. This is the first drop. The second drop would be smaller because of the dilator with sheath here will go down to the area of fossa ovalis over here, right? This is the big drop, and the second drop is smaller because the dilator is in the area of fossa ovalis. Just like this, make a another small drop, the second small drop here. Okay, after the dilator is at the area of the fossa ovalis, the needle puncture, the broken bowl will be advanced a little bit into the interseptum, and then try to puncture the septum and let the needle out into the left atrium. And after that, the doctor will try to identify the location of the left atrium by injecting some contrast to make sure. Okay. Just like that, just like the previous slide, the doctor will, in some center, maybe do transceptor puncture under TEE, transesophageal echocardiography, in order to confirm about the needle that is on the fossa ovalis or in the correct position or something like that. During, okay, start from the picture A. After the dilator and the sheath moving, let's say pulling, is pulled from the SVC, maybe over here, and then make a two drops, right? The first drop is quite big because the dilator will be pulled from the SVC into the atrium. After that, we should see another small drop. That means the dilator is going into the fossa ovalis. Okay. After that, the doctor will confirm the position by the transesophageal echocardiography here. sometimes the doctor will confirm the location again with try to inject some contrast, and the contrast should be in the direction of against, because the contrast will against with the with the fossa ovalis, and the flow of the contrast from against the fossa ovalis should be like this. Okay, that means the doctor can make sure that area is correct and is ready to puncture the septum. During the puncture, the doctor is advancing the broken bone needle from the TE. They will confirm with into the atrial septum tenting that showing on the TE. And after that, after the broken bone needle can pass through into the left atrium, the doctor will confirm again with contrast injected into the left atrium. If the contrast spread out entirely within the LA, that means the catheter is in the LA, the left atrium. But if the contrast is flowing like the aorta into the systemic, that means the doctor is puncturing the aorta, and that caused the aortic perforation, something like that. That needs to activate the operating room to open heart and try to close the puncture site that makes the blood out of the aorta. Okay. After confirming that the catheter within the left atrium, the doctor will insert the guide wire with 0.032 inch into the left atrium, and then remove the dilator and place and leave the only sheath inside the heart, and then the doctor can insert any ablation or special mapping catheter into the left atrium to go on the complex procedure. Okay, well, as I said before, the primary veins, the primary veins are all connected into the left atrium. So the primary veins are, let's say, about a location that can generate the abnormal signal. So in the atrial fibrillation, we often see that the doctor will do primary vein isolation in order to create the line of abrasion around the primary veins, not to allow the abnormal signal from the primary vein to outside into the left atrium. Okay. the left ventricle we often don't use any diagnostic catheter to place inside the left ventricle because let's say again, in the standard procedure, we can use the RV catheter or CS catheter or highlight catheter to place or to stem to do anything to study about the electrogram. If we want to see about the activity in the ventricle, in the left ventricle, we can see from the CS catheter that can show you both intro signal and ventricular signal. Okay. Whenever the doctor need to go to the left ventricle, because that means the doctor need to ablate some abnormality inside the left ventricle. For example, the PVC, the PVC, the premature ventricular contraction that is generated from the left ventricle. The doctor will use the ablation catheter into the left ventricle through the femoral artery, go to the aortic arch to the aortic valve, and then alveoli down to the left ventricle. And that's it. The doctor can use the ablation to ablate inside the left ventricle, as well as about the accessory pathway with it from the left side. The doctor can ablate that accessory pathway by doing retrograde fashion like this from the femoral artery into the left ventricle, or the doctor can do the puncture septum as I described you before to approach the left atrium, and then after advancing the ablation catheter into the LA, the doctor can just deflect the catheter, the ablation catheter, into the mitral valve annulus to find the location of the abnormal pathway. The last one, epicardial space. The epicardial space, it's hardly be seen because the doctor will do when there are some arrhythmia originated from the epicardium, just like epicardial PVC, something like that, or in a patient who has multiple, let's say about polymorphic VT, just like the Tosa-Derpong, that we assume that the origination of the abnormality of, about just like the Brugada syndrome, that we assume we have the theory that of the abnormality of the origination of let's say about that. When the doctor will do ablation, will do epicardial ablation whenever the patient come with epicardial PVC, or in a patient with Brugada syndrome, that we believe that in the patients with Brugada syndrome, the origination of the abnormality that caused the ventricular tachycardia is from the epicardium. So the doctor will do the epicardial approach by puncture at the subxiphoid process in order to access to the pericardial space. And ablate and do ablation on the epicardium. Okay. Well, on the catheter position, when we see on the fluoroscopic images, you can see like this. The picture, the fluoroscopic image, on the top here, is showing you about the PA view. PA means posterior anterior view over here, and the bottom one is the left anterior oblique view. The question is how to identify the catheter inside the heart. We just need to simply just need to identify first here. You can, you have already know that the catheter which is placed at the high right atrium will be high right atrial catheter, right? So this catheter should be high right atrium. And the second one you can guess is that this catheter, the catheter comes with 10 electrodes on the catheter, and the spacing size is 252 millimeter. It should be CS catheter. So this one is CS catheter. Okay. Then about this one, a diagnostic catheter with 4 electrodes, apart from highlight atrial catheter, and it should be the right ventricular apex catheter, or maybe his catheter if the spacing is the same. But when you look at the picture, this PA view, you can see this, the direction of the catheter is going down. We can guess that is the RV apex, right? And the catheter is higher than the RV apex with 4 electrodes on the catheter, which is at the middle of the picture. It should be his catheter, just like this LAO catheter, because in the PA view, you can match this picture with this one. The position of the catheter will be just like this. This is showing you about the PA view. When it comes to about the LAO view, just imagine the LAO view. The patient's apex of the heart will be in front of us, just like this. The apex of the heart will direct to us when you see the the picture. So when the apex in front of you, you can identify that this catheter should be RVA catheter on the quadrupolar catheter within the RV apex, and the upper one should be his catheter. Okay, and these catheter with 10 electrodes should be CS catheter. And again, the high right atrium catheter should be like this, because it is placed at the upper part of the right atrium. After placing all of the catheter in position, if you look at the RV catheter, you will see just a single signal on this line, because the RV catheter will just only receive the ventricular electrogram, and the high right atrium, the high right atrial catheter will just only receive atrial electrogram from inside the right atrium, right? So the ventricular electrogram should be the ventricular electrogram. If you see on the local electrogram tracing, you should see the electrogram inside the QRS complex, just like this. In order to differentiate the ventricular electrogram from the atrial electrogram, because the atrial electrogram will be aligned to the PVEF here. Okay. After that, his bundle catheter, because the catheter is placed between the atrium and the ventricle, so on the catheter we should see the atrial electrogram and the ventricular electrogram as well. Apart from that, you should see about his electrogram, just like the spike signal here between the A and V signal. From this is definitely you as well as about his bundle electrogram or on the catheter of the proximal electrode can see just like the distal one, but because the proximal is often more into the right atrium. That's why the A signal is bigger than the distal one, because the distal one is closer to the ventricle. The proximal one is closer to the atrium. Okay. And the last one, the CS catheter. The distal electrode of the CS catheter, we call it as CS1 and 2, right? But the most proximal electrode of the catheter of the CS catheter, we call it as CS910. So when you consider about the activation sequence or activation activity, that the depolarization of the atrium will come from the right atrium and then go to the left atrium, right? So the atrial signal, the first atrial signal should be seen on the CS910 first, right? Because CS910 is at the ostium of the coronary sinus, and then the activation will go from right to left left side. So the latest latest atrial electrogram should be showing you on the CS1 and 2, which is so lateral. Okay. And again, you can see about the different size of the atrial electrogram and ventricular electrogram. It can tell you the different size. The size of the amplitude of the signal can tell you about the location of the catheter. You can see like this because the CS is more, the coronary sinus location is more in the atrium than the ventricle. So the electrodes on the CS catheter can detect or can record the activity from the left from the left atrium or from the atrium more than can record the electrogram from the ventricle, just like this. Okay. Okay, the last part, the basic electrophysiology study. I just want to describe about this thing just a little bit. Okay, the basic intervals, the thing we should know are rhythm and cycling, the PA interval, the AH interval, the duration of the his bundle electrogram, the HV interval, and the QRS duration and the QT interval. Let's see how to measure that interval. The cycling is starting from ventricle is depolarized and cause the ventricular contraction, right? So we can measure the cycling from the R wave, which is the beat of ventricle is contracting the blood of the body, right? And then you're gonna have to measure this from R wave here to the next R wave. This is one cycle, right? After that, we're gonna have to measure the PA interval. How to measure it? PA interval means we are measuring about the activity from starting from SA node or originating electrical impulses, and then spread out the electrical impulse throughout the both right atrium and left atrium to cause atrial depolarization. So how to measure it? We just start from the the first deflection, the onset of the atrial electrogram in the high-right atrium, and then we will measure until the first intrinsic deflection of the A wave or A signal in his bundle electrogram. In A wave, I'm sorry. Start from the onset of the atrial signal from the high right atrium catheter, and then to the peak here. You can see the peak here. We call it as the intrinsic deflection, the starting of the intrinsic deflection. If you measure over here, you will get the PA interval. That means the activity, the appearing in the atrium from atrial depolarization until the electrogram or electrical impulses go to the AV node. Okay, this is the atrial electrogram at the AV node, right? After that, we can measure the AH interval. The AH interval can start from the first intrinsic of the A wave or A signal in his catheter, and then go to the before the onset of his spike here, so we can get the AH interval. Next, we can some EP labs maybe measure about his bundle electrogram. We can just measure from the onset of his electrogram and then cover until the end of his bundle electrogram. We can see about we can tell about the activity at his bundle, that is normal or not, because normally it should be less than 30 milliseconds if you measure his bundle. Okay, but actually not commonly. You are probably not seeing in the real lab, because not common to measure in the lab. Okay, next, we're gonna have to measure the HV interval to see the activity from the electrical impulse from his bundle until to the Purkinje fiber. Okay, we can start measuring from the onset of his bundle of his electrogram until the onset of the QRS complex on the surface or body surface EKG. Or you can use the RV catheter to be reference to measure, but you're gonna have to make sure that the ventricular electrogram on the RV catheter is the earliest ventricular signal. Is it true? Okay, if it is the earliest ventricular electrogram, it could be used to measure as a HV interval, just like this. You can see the line here. this is the onset of QRS complex, and definitely this is the onset of the reticular electrogram as well. But in the real lab, if you cannot see the earliest, the RV signal, we recommend to use the onset of the QRS complex instead in all cases to measure the HV interval, okay? Next, we're gonna have to measure about the duration of the QRS complex. And the last one, don't forget to measure the QT interval by measuring starting from the onset of the QRS complex until the end of the T wave. Okay, but if you wanted find more the QT interval, which is in the lab, you gonna have to calculate the corrected QT interval by using the QT interval divided by the square root of the RR interval, because the QT interval normally can be affected by age, by gender, and the variety of the heartbeat, let's say that. Okay, this slide, I just want to show you about the normal value from you measuring the interval. This is of this value, you're gonna have to can remember of this, because when you can work in a EP lab, you will be able to assess or to find the abnormality more faster. Okay. Okay, finish. Anybody have any questions?มีคำถามไหมครับผม
ยังไม่มีค่ะอาจารย์
โอเคไอ้ตรงนี้ไอ้ basic interval นี่พอเข้าใจเนาะไม่รู้ว่าอธิบายเข้าใจหรือเปล่าในภาษาอังกฤษเพราะว่าที่เอามาตั้งใจเอามาเพราะว่ามันค่อนข้างสำคัญในเรื่องของ basic intervals นะครับโอเคงั้นถ้าสมมุติว่าไม่มีคำถามแล้ว ถ้าสมมติสงสัยอะไรตรงไหนฝากคำถามถามพี่ฉายมาได้นะครับ เดี๋ยวพี่เหมือนเดิมเนาะเดี๋ยวจะพยายามหาคำตอบไปให้นะครับนะ
โอเคค่ะขอบคุณค่ะ
โอเคครับงั้นขออนุญาตจบเซสชั่นประมาณนี้เนาะขอบคุณมากนะครับถ้าเกิดว่าพูดไม่รู้เรื่องอะไรตรงไหนต้องขอโทษด้วยนะครับ
ขอบคุณค่ะอาจารย์ขอบคุณมากเลยค่ะอาจารย์ขอบคุณค่ะอาจารย์ขอบคุณมากค่ะ
ขอบคุณครับบ๊ายบาย